A programming model describes how the CPU operates. Programs operate on values stored in variables. Computers store these values in memory. CPUs operate on data values through registers. The instruction set architecture defines the operation of the computer. It includes how instructions are formatted or how they're represented as bits. It also includes the definition of what these instructions do. And it includes the formats for data. Many computers operate on the von Neumann model, in which we have a single memory that holds both instructions and data. The CPU fetches an instruction from memory and executes it. That instruction may cause it to operate on the memory to change a value. The Harvard model is another useful model. In this case, we have separate memories for instructions and data. The von Neumann model doesn't distinguish directly between instructions and data. The program counter for the CPU points to a given location. It interprets that as an instruction. If a memory address register points to that same location, it's interpreted as data. Different computers use different ways of organizing bits into words in memory. Here are two different orders of bytes in a 4-byte word. The top starts with byte 0, the bottom starts with byte 3. A big endian representation puts the least significant bit at the lowest position in the word. A little endian representation puts the least significant bit at the highest location in the word. So long as we're consistent, it doesn't matter whether we use little endian or big endian. But when we transfer data from one computer to another, we need to make sure that either they both use the same representation or that we adjust accordingly. Boolean algebra is the building block of operations in a computer. Boolean operations are useful in themselves to represent truth values and logical operations. We can also use Boolean algebra to build operators such as addition. Some traditional Boolean operations include and, or, not, and exclusive or. Mathematicians have one way to write these operations. The C programming language has another. We can use truth tables to define these operations. The left-hand entries in a row in the truth table represent the arguments to the function. The rightmost entry in that row gives the result of the operation. As with arithmetic, Boolean algebra follows certain laws. Operators associate, they commute, they distribute. One very useful operation in Boolean algebra is De Morgan's law, which allows us to move negation. We can also make use of double negation. Not A is equal to A. We make use of two types of don't cares in Boolean algebra, but they're very different. An input don't care is simply a notational convenience. In this case, we have the same output for the function whether the B input is 0 or 1. We use the dash to denote that either case gives the same result. An output don't care is an incomplete specification of the function. Here, the input combination 1, 1 gives an undefined output, which we represent as X. We'll see later that output don't cares can be useful in optimizing logic. We can create Boolean algebra functions that perform arithmetic on binary numbers. Here we have a truth table with 3 inputs, A, B, and carry in, and 2 outputs, the sum and the carry out. The sum is the exclusive or of the 3 inputs. The carry out is true when at least 2 of the inputs are 1. Given the functions to perform sum and carry for 2 1-bit operands, we can extend to a 2-bit addition. This simple form of binary addition is known as ripple carry because the carry out ripples from one bit to the next. We can optimize the logic for addition using more sophisticated algorithms. It's useful to define operations on some integers. We use them for our programs. We can also use them to guide the execution of the machine. The 0 function is true when none of the bits in the operand are 1. For 2's complement numbers, the number is negative when the most significant bit is 1. A number is positive when it's not negative and it's not 0. And 2 numbers are equal when an XOR test on every pair of bits comes out to be 0. We can define an overflow operation for 2's complement numbers. Adding -1 and 1 does not result in an overflow. Adding -8 to -1 gives us a number that is more negative than what we can represent in 4 bits, which results in an overflow. Adding 7 to 1 gives us a number that is more positive than what we can represent, giving an overflow. Thanks for watching.